Find the possible equation for the rational function below. Now, a rational function is nothing but a polynomial divided by a polynomial. And polynomials can be written in two ways at least. You can think of them in factored form, something like 5 times x minus 2 squared times x plus 3, or standard form. And I'm not going to multiply this out. I'll give another example, 3x cubed minus 4x squared plus 7x minus 3. Now, this is the one that's easier to interpret. This is the one where geometry and algebra can be translated to each other nicely, because this is the one when you work with factored polynomials in factored form, it's easy to see the zeros thanks to the zero product principle. So if x is 2 or x is negative 3, this polynomial becomes 0. Whereas, and at the bottom, the standard form, we have to use more advanced ideas like rational zero theorem. So getting from standard to factored form was a topic that we spent time with. Anyway, so what I will be doing is I'll be making some observations from this graph and try to discover some factors, both on top and at the bottom. And the way the factors on the denominator and the numerator, the role they play, is as follows. The factors of the denominators, they're responsible from the domain. So you start with the bottom of the rational expression. So, for example, if your graph, if your function is 1 over x minus 5, then the graph is shift the graph 1 over x, right? That's one of the toolkit functions we're familiar with, to the right by 5. So we have a vertical asymptote at x equals to 5. Whereas if you have a 0 that can be simplified, then that just means your function is still not defined at x equals to 5. If your function is x minus 5 over x minus 5, when you plug in 5, the denominator becomes 0. But that, it turns out that those factors can be cancelled out for this example, and everywhere except x equals to 5, the function is the constant function 1, except at 5, you don't have an output. That just means you have a missing point. So those are the two things that can happen, whether you can simplify the 0, the factor at the bottom, or not. And you either have vertical asymptotes or holes on the graph. On the other hand, if you have a factor of the denominator, you can easily find zeros of the numerator. And if you have a factor like x plus 7, then at negative 7, you get 0 over some non-zero number. In this case, what are those? 9 times 4, whatever it is, this is going to be 0. But it's important that you have to make sure the denominator is not 0 at the same time. Like here, for example, 5 is a 0 off top, but we first deal with the denominator, and then we say, oh, 5 is a number that you can't use. It's not even in the domain. It makes the fraction not defined. So you start with the denominator, then you work with the numerator when you have a rational function. Always the domain is where you start with. Anyway, so what are some interesting things that are happening? So I have a vertical asymptote at negative 2. I have another vertical asymptote at x equals to 2. I have a 0 at negative 1. Negative 1 comma 0 is a 0, is an x-intercept, and 1 comma 0 is another x-intercept. And then I look and see, wait a minute, this graph looks like even. So if I plug in negative x for x, I get the same function. Or if I fold along the vertical axis, then I reflect along the vertical axis, I get the same graph. And then there's one last piece of interest. There seemed to be a horizontal asymptote as the end behavior, and it seems to be y equals to 4 at both ends. So the blue pieces of information, the red and the green, from those I will try to form my function. And maybe some scaling will be relevant, so maybe I'll add one more color, and maybe we just use it for I think that's not going to be necessary, but it won't hurt to put it there. I don't even know this number. Is this 1? Maybe not. I'm not going to, I think it looks like 1. Let me just put it and see what happens. Anyways, so let's start with the blue informations, pieces of informations. We have 2 vertical asymptotes. At x equals -2 and x equals to 2. So the vertical asymptote at x equals -2 will give us a factor of the form x plus 2 or x plus 2 square, or maybe a higher power. So the graph of something over x plus 2, if -2 doesn't cause any other issue, is around x equals -2, the graph looks like that. And if you have x plus 2 square, around x equals to 2, the graph looks like that, or the flipped versions, depending on what's happened other than this factor. There could be potentially a vertical reflection, because maybe this quantity becomes plus or minus at -2. That I'm not interested at this point. We'll figure it out later. And then I look at my graph. Oh, my graph looks like this. So that's not the case. So I have x plus 2. I'm going to put x plus 2 in the denominator. And I'm going to keep it simple. So x plus 2 cubed is another possible. The graph kind of looks like that, near -2. But this is unnecessarily complicated at this point. So I'm not going to take that. I'm not going to start with that. And probably you won't need that either, but we'll find out. If our choices doesn't produce the graph that we want, we can modify, and that's maybe one thing we may do. Probably not. And we have similar thing happening at x equals to 2. And that means I have another factor, x minus 2, in the denominator. And then I look at the x-intercepts. I have one here, x at x equals -1. I have an x-intercept. And so x plus 1. And there could be other things around, other factors around. And what this will do, what this will cause is near x equals to -1, when I zoom in, I'm going to see the graph kind of looks like a line. Y equals to x shifted to left by 1. Or maybe my graph looks like this, right? Like a quadratic function shifted to left by 1. So, and there could be other factors around. Or higher powers, of course. And then from those candidates, I'll pick the one that that looks like my graph. And here, when I look at it, it kind of goes straight, right? There is no curvature change. So that seems to be the case, except my graph looks like this, right? But that's fine. So these two are related by vertical. Oh no, that is my graph. But my graph maybe could have looked like this. In both cases, I would have picked this x plus 1 in the denominator. And these two are related by a vertical reflection. And x plus 1 doesn't care about that, doesn't have that information. The other factors will have that, plus or minus. So I'm going to put an x plus 1 because of this x-intercept. And for this x-intercept, I'm going to put a x minus 1. So far, this is how my function looks like. Now let's look at the horizontal asymptote. Now, when I work with large values of x, then this expression will look like, well, x plus 1 will look like x. X minus 1 will look like x, because what happens if you subtract 1 from 1 billion? Doesn't make a change. It's insignificant. And x squared over x squared. So my outputs will be like 1. This is not what I want. I want my outputs to be like 4. So what am I supposed to do? Well, I'll just multiply whatever I have by 4. Okay. And that's the contribution of the horizontal asymptote. And just to check, I think this is good enough. I will check the answer key shortly. But f of 0 is going to be 4 times plus 1. Wherever I see x, I plug in 0, right? 2 times negative 2. And minuses cancel each other out, and that is 1. So this is actually consistent with my y-intercept. If it wasn't the case, well, that would be problematic, because I can't use a vertical stretching. I can't use this trick again. That if I multiply by another number, that would change the horizontal asymptote. So I would multiply by a number and then do a vertical shift. Like I would subtract, maybe multiply by 8 and subtract 2, and then I would combine the fractions. A little messier, but the question doesn't go into those territories. So let me quickly check the answer on the answer key. And it is good. So this is my function.